Okay, so in the next example, we'll look at another position function of an object moving in one dimension. And in particular, we're going to look at how the position graph can be used to determine the object's path of motion. Really what that means is where exactly the object is at each point in time. That's really what the path of motion is. So let's just jot down a comment about that. So where the object is at each point in time. So that's what we mean by path of motion. Okay, so let's jump into this example. What's happening? So we've got a bug, and it starts at the origin of R. Remember, this is the real line, right? So this is the picture down here. You can see the bug is starting at the origin of the real line, and it begins crawling along the real line with position function given right here, right? We're given the position function is s of t is given by the sine of pi times t over 2. So it looks like it's a compressed, or in this case actually a stretched sine wave, where t is given as the time variable, as usual, but it's measured in seconds since the bug first left the origin. Okay, so this tells us how to interpret the time variable t. And what else did it say? The position graph of the first 4 seconds of movement, so in other words, between t equals 0 and t equals 4, that would be the first 4 seconds of movement, is given below, along with a sketch of the bug's path of motion. Okay, well here's the position graph. That we truly are given the position graph, but the path of motion is not actually here. It says the path of motion is here, but it's not. So it's going to be up to us to actually fill in that path of motion. Okay, so, well, let's look closely at the position graph. What does this mean? Well, look, you got the t-axis is your horizontal axis, and then the y-axis is your vertical axis as usual, but y is actually equal to s of t. So the y-coordinates of these points tell you the position of the bug at the corresponding t values, right? So for example, this point here corresponds to t equals 0, and the y-coordinate of this point is 0. So that tells us that s of 0 is equal to 0. So in other words, the bug's position at time 0 is right at the origin. And really, we already knew that. That was told to us in the question, right? The bug starts at the origin. But it's nice to know that this function definitely corroborates what we're already told. So what happens in the first second of motion? Well, the first second of motion really corresponds to this segment of the graph, right, between t equals 0 and t equals 1. Once you get to t equals 1, that's the end of the first second of motion. So what's happening to the y-coordinates of the points on the graph during that first second? Well, they're increasing, right? Here the y-coordinate is 0, and as I move to the right, up to the point t equals 1, the y-coordinates go from 0 and they increase until they get to positive 1. So really what that means is during the first second of motion, the bug is walking over here, and then it gets to the point 1 on the real line. Okay, so let me just include this t equals 1, and I'll draw an arrow just to indicate that this is where the bug is at the point in time t equals 1, right at the end of the first second of motion. Okay, well let's keep going. What happens during the second of motion? So as t goes from 1 to 2, that's really the interval of time that corresponds to the second second of motion, right? The number 2 second of motion. Well, what happens to the y-coordinates? You start at 1, which is where the bug is right at time t equals 1, and then the y-coordinates decrease down to 0. So what that means is the bug turns around and walks back to the origin. So at time t equals 2, at the end of the second of motion, or at the end of the first 2 seconds, let's say, the bug is back where it started at the origin. So this right here corresponds to t equals 2. Okay, and I just want to be clear, it might be misinterpreted by somebody who looks at this drawing and thinks this looks like the bug is actually flying up and taking off and lifting off of the real line. That's not what I'm intending to communicate here. You can imagine that if I just drew the path back over top of the bug, it might get hard to read. And by the time we're done this picture, you'll definitely see why I wanted to draw it a little bit higher. So this is to be understood as the bug walks over to 1 and then turns around and walks back. So just because I draw the path increasing a little bit upwards, it's only to make it clear and easy to read. It's not to indicate that the bug is actually taking off, because the bug is moving in one dimension. It's moving to all it can do is move to the left or the right on the real line, right? Because it's moving in one dimension. Okay, let's do the third second of motion. We got t equals 2 to t equals 3. This interval of time corresponds to the third second. Well, what's happening to the y-coordinates of these points? They start at 0 and they decrease down to -1. So that means the bug, as it's walking this way, now as the third second begins, it keeps on going all the way to the point -1. And then that's where the bug is, at the point t equals 3. Okay, so that's where we are at this point. We're at where the bug is at, has a position of -1, but then as the last second transpires, or the fourth second, the y-coordinates increase from -1 all the way up to 0, so the bug heads back to the origin again, and then finally stops. And the bug stops at t equals 4. Or at least, for the purposes of describing the first 4 seconds of motion, that's really all we know. That's where the bug is at the end of the 4 seconds. Okay, so that's what it means to have a path of motion. But it is a common misconception that when people look at the position graph, they confuse this curve as the path of motion. But no, that's not. This curve is not actually the path of motion. The path of motion is just in one dimension. The bug's walking back and forth across the real line. But this is the graph of the position versus time. So it's a graph of the position graph, but this is not the path of motion. Okay, so next, I hope I've given you a reasonably clear picture of what position functions are and how their graphs correspond to paths of motion. And next we'll talk about types of velocity. And there's 2 different types of velocity we're going to discuss. So first of all, the average velocity, which you would consider over an interval of time values, and then the instantaneous velocity, which you would consider at a particular point in time. So we'll start with the average velocity, and in order to define it, you're going to need to have an object moving in one dimension, which we have here, right? Suppose that an object moves in one dimension, and you're going to need a position function, which is given here as s. So let's assume we've got all that. You can think of this as an example, right? You can think of this in the background. You've got some object moving in back and forth along one dimension. It could be this bug, and it's got some position function, which could very well be this position function up here, but it doesn't need to be. This is general. Okay, so we're going to define the average velocity, which, like I said, the average velocity is to be considered over a time interval from 2 time values, say t0 to t1, right? So this is to be interpreted as a closed interval of points of time between t0 and t1. So t0 is the first point in time in the interval, and t1 is the last point in time in the interval. And by the way, you'll often hear people say t0 as opposed to t0, and it's standard to call it t0 as a particular value in this case. So what's the definition of the average velocity over this time interval? Well, for the notation, we write the letter v, and then in subscript, we're going to put just the 2 letters AV, just short for average. So it's the velocity. Oh, by the way, it's the average velocity. That's how you should read this notation. And how it's defined is using the following fraction. We're just going to take s of t1 minus s of t0. And first of all, by the way, really, we're not done yet. I'm going to add more, but first, really quickly, I want to identify what this actually is measuring. If I just look at this piece, what this is s of t1 minus s of t0. That's the position at time 1 minus the position this is the position at time t1 minus the position at time t0, which is really the net change in position. Over this time interval, right? That's what this is really actually measuring. Okay, but then we're actually going to take that quantity and we're going to divide it by t1 minus t0, or t1 minus t0. And what this really is really the length of time in the time interval, the change in time between time t0 and time t1. So this is the change in time. So the reason I want to highlight that is because this should be somewhat of a familiar formula to you if you took any physics course in high school. A lot of times you'll talk about the average velocity as a change in position over a change in time, or sometimes you might hear change in displacement divided by change in time. This is really nothing different. This is the exact same thing. Let's draw the picture. So the picture looks like the following. Let's draw just maybe do a sketch of what the position graph might look like if I have a t-axis and then I have a y-axis. If I'm drawing the graph of y equals s of t. This is just to clarify that this is the graph of the position function. And let's say it had something like this. Right, I'm just drawing any old curve. It doesn't have to be like this, but it certainly could be like this. Let's say you had that graph, and maybe I'll draw a point t0 here, and then t1 here, maybe something like that. Well, each of those time values correspond to a point on the curve. Right, so the y-coordinate of this point is actually the position of the object at t0. This is s of t0 right here on the y-axis. So we can label that. And then whatever the y-coordinate at this point is, which would be over here, that's going to be s of t1, the position of the object, the position of the object at time t1. So what you're really doing here, the reason I wanted to draw this picture, is I want to point out the fact that this average velocity, when you compute this fraction, what you're really doing is this is the slope formula between these 2 points. You're talking about the change in the y-coordinates divided by the change in the x-coordinates, or in other words, it's rise over run. You're talking about the slope of this line. So I just want to add that in just for emphasis. That's really what you're calculating. So let's write a comment up here. The average velocity is the slope of this secant line. Okay, and I call it a secant line because it is a secant line. What is a secant line? It's just a line that goes through a curve at 2 points. You can see it does. It goes through the curve at 2 points here. So that's why it's called a secant line. Okay, so that's what you're doing when you calculate the average velocity. You're really talking about, it really just boils down to rise over run.